First of all, thanks for joining my session about the Microsoft Query Optimizer. And before I start the session, I just want to introduce myself. So my name is Torsten Strauß. I'm an MVP from Germany, specialized in SQL Server performance optimization. And that's me. So you can reach out to me whenever you have questions. So this is my email address, my website, everything you need to contact me. So let me close this session. First of all, and I also want to thank the sponsors, which you can see here. Without having the sponsors, these kind of events are not possible. So that is really something I appreciate, that even in these hard times, we have these events available. It's really great. Okay, perfect. Let's start. Let me, this is a little bit annoying. Okay, perfect. Yeah, so I just want to prepare the session. So I will use AdventureWorks 2017 for the demonstration. So nothing special. It's a database we all have, or at least we can download. Just want to set statistics.io on, and that's it. So we can start. So the first thing you need to understand is that the query optimizer in Microsoft SQL Server is a cost-based optimizer. So, and the costs are calculated based on CPU, memory, and I/O consumption only, which is sometimes or the other way around. The cost which you can see in an execution plan, this is really not the actual cost. This is just an estimation, because as we will see, the query SQL Server needs in order to execute as a plan which is created in order to execute a query is something which happens before the actual execution of the query. That is a reason why the query optimizer has to estimate the cost. So that is a reason whenever we will see execution plans later in the demonstration, the cost which we will see on the select operator are just an estimation. They are never ever the actual, and they are never ever the accurate costs. So my recommendation, honestly, is do not rely on cost in order to compare plans with each other. It is much more important to compare I/O and CPU time, not elapsed time, as we all know, because elapsed time also includes wait statistics. So a query can wait for resources, and therefore the elapsed time, the overall elapsed time, is also not, I would say, a KPI which I'm using for query performance tuning. So cost is something which is, I would say, maybe good for comparison, but never ever in order to decide whether a plan is good or not. So that is something you should understand, right? So the other thing you should know is that the query optimizer, the calculation and the estimation of the costs are considered based on physical I/O only. That means the query optimizer always assumes that the data are not in the buffer pool, which is which is not the truth anymore, because most of the instances we have a lot of memory available. So it is very likely that the pages are in buffer. So we do not have any kind of logical I/O anymore. So just when the pages are read the first time from disk, they are going to the buffer, and then the query execution or the query engine can take the pages from there. So, but nevertheless, so the query optimizer always assumes that the data are not in cache, and that can lead to non-optimal plans, and that also will lead to completely wrong costs, right? Because the I/O costs are always part of the overall cost estimation. This is, by the way, completely different in the memory OLTP, because in the memory OLTP, the assumption is that all the pages, we do not have pages anymore, we have just records, are in memory, and there's never ever any need to read data from disk. Okay, let's talk a little bit about the phases. And when we talk about phases, I'm talking about the steps the query optimizer has to do in order to create a valid and a so-called good enough plan. So we have something which is called parse or parsing. So the output of, and we are going more into detail, but parsing is nothing else than to create a parse tree which checks the syntax. Then we have the algebraizer tree. So the phase is binding and the output is the algebraizer tree. We will see this later on. This is, I would say, a logical representation of logical operators. So then we have the query optimization. So in the output is the execution plan, which is used in order to execute the query. And in most of the times, the execution plan is cached in the plan cache. And then we have the query execution itself. So that's it. So in order to understand the dependencies or the dependency for the query optimizer, we can use DBCC optimizer what if. So DBCC optimizer what if will tell you the dependencies of the query optimizer. So we can see the query optimizer is based on or dependent on the CPU settings, memory, whether it is a 32 or 64-bit version, the parallel cost threshold for parallelism, and so forth. So we have a lot of dependency. That means when you're running a query on your machine with a specific hardware configuration, the plan can look different in another environment, depending on these kind of resources which are available. Yeah? Let's say we have a 2-core machine. SQL Server can create an execution plan for sure, but when you move your plan to an instance with just 1 core or maybe, I don't know, 16 cores, the plan can be completely different, right? That is also the reason whenever you test your application, you should be, or the test environment should be the same as your production environment, because otherwise the query plan is not the same anymore. It's very likely. So I will give you an example. So this is a query which we can easily execute, and because I allow degree of parallelism of 8, so max DOB, SQL Server already detects that the cost or the estimated cost of the query is high enough. So we can see that it takes a moment. Sorry for this, but we can see this is a parallel plan based on the cost estimation. And the cost is something about 333, which is more than I configured as a cost threshold for parallelism, which is 50. So therefore, SQL Server parallelizes the query. So now we can simulate what happens when we just have a 1-core CPU machine. So we can easily do this with DBCC optimizer what if. And this is the first property, which was CPU. And we can say we have only 1 CPU available. We are just simulating another hardware. And this also works the other way around. We can even use optimizer what if to simulate that we have, I don't know, a 16-core machine, even if I have only a 2-core machine available. So that is very helpful in order to simulate the query execution plan on another hardware configuration. So let me execute this one. And when I execute the same query again, I do not need to execute the query actually. I just need to see the execution, the estimated execution plan. This query is not running in parallel anymore because it has only 1 core available. So, and that is very helpful. Again, optimizer what if really helps you to understand how your query plan will look like in another hardware configuration, right? So let me reset all the warnings, all the settings. Just want to make sure that everything is reset. Perfect. CPU is 0 again. That's perfect. So let's talk a little bit about parsing. So the output of parsing again is the parse tree. That's very easy to remember. So during parsing, SQL Server just check the syntax. Yeah? If the syntax valid or not. If the syntax is valid, the query optimizer will go to the next step. If the syntax is not valid, for sure, SQL Server will completely stop query optimization because the syntax is invalid. So we can easily see this. We can simulate the parsing of the query optimization by set parse only to on. And sorry. So the SQL Server will not execute the query anymore, just parse the query. So we can see this, the table exists, so parsing is successful. So the table exists, and but the column is not part of address. Parsing is still successfully. So the table does not exist, parsing is successfully. So neither the column nor the column exist, the table nor the column exist, parsing is successfully. Parsing is really just to check the syntax, nothing else, right? So the next tree, the query optimizer, or the next step the query optimizer takes is it will create a so-called algebraizer tree. So it will bind the logical representation of the object, which is in this case person address 1, to the object within your database. So it makes sure that the columns and the table exists, at least for the early binding phase. So we have in stored procedure, we can have something like a late binding. So here tables do not have to exist at the moment the stored procedure is created but executed. But most of the queries we see in SQL Server have something which is called early binding. That means the table and the columns must exist. So the next one is the execution plan. And the execution plan is something where we will dive into later on. So this is nothing else, or nothing else, I would say this is really the execution plan the SQL Server engine will use in order to satisfy the query. So the storage engine for sure receive all the needed information from the query engine in order to scan a table, to seek an index or whatever. So this is a physical representation of your query. Yeah. So some kind of instructions for the query, for the storage engine of how to get the data. So we will see this later on. So and in the end, we have a cache plan. Most of the plans are in cache. Some of them are not. We will see an example later on. So let's start with the different trees, and we are going a little bit more about into detail. So when SQL Server parses the, I would say, the algebraizer tree, it will start with further simplifications. So we have something which is an input tree. We have simplified tree. We have a join tree. We have a tree before a project normalization and after. Then we have something which is called an output tree and a tree copied out. So and we will see all these kind of trees later on. So you already understand that query optimization is a really complicated subject, and therefore SQL Server have to ensure that during the query optimization, several steps are happening in order to simplify the overall complex query to reduce the complexity, right? Because in the end, the simpler the query is to execute, the better the performance will be. And that is always the goal, simplification. Okay, so the simplification is, for example, we can detect trivial plans. We have cost-based optimization. And once again, this is based on cardinality estimation, on the statistics, right? And we have something which is also called auto-parameterization in order to avoid that SQL Server always have to recreate a new plan. So the idea is to reuse an existing plan and just execute the parameters. For example, you have a predicate where product ID is equal to 1 or whatever, then 1, so the constant is replaced by a parameter. And so the plan can be reused when the next query is, for example, asking for product ID 2. It's just replacing the constant, replacing the parameter, but not creating a new plan anymore. So we can see all these kind of trees here with DMXE, which is an extended event, DMV, map values. And you can see there's even something available. So we can see all these kind of trees available in SQL Server. So it's not a secret when you know where to look for. Perfect. So the next thing is, let's talk a little bit about the algebraizer tree, because again, this is the start of the journey. So we have one query trace flag, which is 8605, which shows the algebraizer tree. So the algebraizer tree, you can see it here. This is the algebraizer tree. It's called the converted tree. And this is, again, just a logical representation. We are talking about logical operators. We do not have a physical representation. It is not about, I don't know, it is not a nested loop. It is not a hash join, or it is not a stream aggregate. It is just, I would say, a logical representation of your query. So you can see something like a log op get. This is a logical operator to get data. So we have a comparison. You can see, because we are comparing data where product ID is equal to 1. This is a comparison, and it is an equality comparison. Again, this is just a logical representation of the select statement, right? Which is now taken from the next tree in order to simplify the query execution. So the next, this is so annoying. Sometimes I cannot. Okay, it works. So another query where we use a left join from an algebraizer tree. This is also just a comparison. You can see it is still a comparison. We are comparing two columns from two tables, from product and product subcategory. And again, this is just a logical representation. It is not about the join we are using. Okay, so the input tree now takes the converted tree in order to add specific metadata to the objects. So we will see this with query trace on 8606. And here we can see we have the input tree based on the algebraizer tree. And it looks like the algebraizer tree, but we have a lot, or we have some more metadata. This is just a small query, so therefore we can see only some of them. We have, for example, the binding. So we can see that the query, or the logical, the converted tree is now translated into the objects which are used in the query. For example, the table production product. This is the internal ID, it's the object ID. So this is the binding phase, right? So once this is done, SQL Server can go ahead with the next tree, or with the next step, which is simplification. So we have different kind of simplification available, and SQL Server has a lot of rules, as we can see later on, in order to reduce the complexity of a query. So let's start simple. So we have something which is called constant folding. We have something which is called predicate pushdown. SQL Server is able to rewrite subqueries, simplify joins, and detect a contradiction. We will see this later on. So let's start with constant folding. What is constant folding? So constant folding is a term which is used from SQL Server to try to evaluate an expression before the query is compiled. So let's start with an example. So this is a query where we have a where predicate, and we can see that we have a calculation in the where predicate. So SQL Server is now for sure trying to evaluate the predicate before the execution, because there's another example we will see in a minute. This helps SQL Server to compare the product ID with the value, which is in our case 317. So otherwise, the query cannot use the index anymore, as we will see. So this is a very simple example where we can see a constant folding. We can see the constant folding here. We can see that the value is now translated to 317. So this is, by the way, an index seek operation, clustered index seek. This is a searchable argument. So Uwe told me yesterday he had a presentation about searchable, as a SARC searchable arguments. And this is a good example for a SARC argument, right? So there's another example this way around. It's exactly the same. It leads to the same product, which is product ID 317. But this time we can see that SQL Server is not able to fold the query, to do constant folding, right? So this time we have an index scan with a residual predicate, as you can see here. So that means the entire index is scanned. And after the scan is done, SQL Server will apply the residual predicate in order to find the product ID, or the predicate, which you can, this is a little bit annoying, the predicate, the filter, which is applied here. This is completely insufficient, or it is not. I would say this is really comparing to the other query where we use an index seek. Here we have an index scan. So just by rewriting the query, you have a complete different plan. This is not a very good plan. Okay. So the next one, I will skip this one. I will clear the procedure cache again, and I will create, or I created already a few queries. You can see one with constant folding, another one with constant folding, and another one. And this query cannot use constant folding, as well as this query. So I will execute two queries with constant folding and two of them without constant folding. Let me do this. So in the end, we can see in the plan cache that, let me do this first of all, that we have one object, one plan, which is prepared. And this is a one which is used, or which is created by the query plan, which was able to fold the constant. So we can see the parameterization here, right? So this plan can be reused by any query which looks the same and uses constant folding. For all other queries without constant folding, we can see that we have just an ad hoc plan, but not a prepared plan. So therefore, query without constant folding will always go to the query optimization, because there is no plan available if you rewrite the query and you have another constant in your predicate. That means you will end up with plan pollution. Yeah. Just by rewriting the query, you can avoid plan pollution, and you can skip the entire query optimization phase, because a plan already exists in your plan cache. Okay. Right. So the next one, the next simplification is predicate pushdown. So SQL Server is keen on removing data. When I'm talking about data, I'm talking about pages very early in the query execution to avoid I/O. So logical or physical I/O, memory and CPU. For sure, if I reduce the number of pages, yeah, which I need to get from the physical MDF file, yeah, if I'm able to reduce the pages, I'm also reducing the memory footprint for sure, right? Because I do not need to send all the pages to my data cache, and therefore I need less memory. So that is the reason why SQL Server always tries to reduce the pages and also reduce the IOs, and it will work like this. So we have the same table, product or production product. We have an execution plan here. And the execution plan is a clustered index seek. So I cannot move the mouse pointer, but you can see there on the bottom of the card, there's a seek predicate. So the seek predicate is something the storage engine already applies to the balance tree, right? Because we have a clustered index, so we are seeking within a balance tree, and we are looking for this predicate. In the end, we can see that we only have two logical reads, which is the root page and the leaf page of the clustered index. Great. So when I force SQL Server to use the heap instead, or the heap, so we can do not use the clustered index. We do not have a heap, but we have another index available, which is the clustered index scan in our case. So you can see the residual predicate in the middle of the card. So therefore, it will tell SQL Server, scan the entire index and then look for the predicate, which is not a predicate pushdown anymore. So we have a lot of pages in memory in our data cache. And when the data are available in the data cache, SQL Server can apply the filter on top of it, which is, we can see we have a logical read of 15. So that is how predicate pushdown works. So whenever possible, SQL Server tries to reduce the number of pages on the storage engine already. But if it is not possible, SQL Server have to read the entire index, the entire table or whatever, and then it will apply a filter on top of it. There's one query trace on which you can use, or query trace flug, which you can use, which is 9130 to visualize the filter. This really helps. So honestly, when I tune queries, I always set the trace flag, because you do not need to look for residual predicates. This time you can see, it's the same query, by the way. You can see in the filter object, filter, it is called an operator or iterator, depends. Yeah, some books are talking about operators, some books are talking about iterators. In the end, it is a filter. So it's exactly the same query, but this time you can see it will scan all pages from the index, and then it will apply the filter. I think from a visualization perspective, that is much better. It is much more understandable, and you can already understand that you have a performance problem here, right? So it is definitely worth to create an index on top of it in order to allow SQL Server to filter the data already on the storage engine. Okay. So let's talk a little bit about rewriting subqueries. So there are a lot of discussions in forums where people ask the question, if there is a difference between using joins or using subqueries. And yes, there is, but not, I would say in 95%, there is no difference. And when I talk about subqueries, this is an example. So the idea is select all from customer where customer ID is equal, and this is the inner query, the inner subquery, which is evaluated first, and the result is now used for the outer query to filter the sales customer. So let's give it a try. So in the end, we can see from an input tree perspective, this is really just a comparison between the customer ID. And from an execution plan perspective, we can see that SQL Server is now able to translate, or to translate the right word, yeah, maybe, or transform. I transform the subquery to a join. So it really doesn't matter whether you write a subquery or a join. You can, for sure, you can create the same query as a join or rewrite the query as a join, but SQL Server already detects that the subquery can be rewritten by using a nested loop. So there is no need to rewrite your queries, right? This happens during simplification. So let's talk a little bit about simplified joins. So SQL Server tries to transfer an outer join to an inner join and remove redundant joins due to foreign key join elimination. So let's see how it works. So this is an example of a query where from a logic perspective, I ask for left join. So you can see from sales customer left join sales order header. Then I have I would say the on predicate. But because I have another predicate where sales order ID is not null, this is from a logical perspective, not a left join anymore. It is an inner join. So in SQL Server is smart enough in order to detect that the left join is not a left join anymore. Instead, it is a so-called logical operator join. And before the simplification, it is considered as a logical operator left outer join. So we can see this for sure in the input tree here and in the simplified tree, but we can also see it in our query execution plan. So in this case, you can see that SQL Server has a physical operator, which is a merge join, but you can see that the logical operator is an inner join. You can see it here, inner join. It is not a left join anymore. So SQL Server, again, is smart enough in order to detect the contradiction here, which we have, right? So this is a predicate in combination with a left join. This will lead to an inner join. Foreign key elimination, that is really something which can boost your performance. So I will give you an example. So we have one query here. So this time I'm using an inner join between customer and sales order header. And the idea is now that I will sum up the total due from sales order header and will group by sales order ID, but just for customers which are part of the sales customer table, right? So this is the required result. So the execution plan shows that only the sales order header is used to satisfy the query. Why? Because we have a foreign key. We have a foreign key between the sales order header and this, the customer table, the sales customer table. And the foreign key already ensures that you only have customers in your sales order header detail table where you have a record in your customer table. So from a query engine perspective, there is no need to use a join anymore. Because of the foreign key, SQL Server can completely skip the step to search or to check and confirm that the customer we have in our sales order header table is part of the sales customer table. There is no need because of the foreign key. So that is one of the reasons why this it is so important to create foreign keys between tables and have a consistent entity relationship model, right? So when I now drop the constraint, so the foreign key, and I execute the same query again, we can see that this time the query looks completely different because SQL Server have to implement a join and inner join, a physical operator, a hash match, in order to ensure that the customer from sales order header is part of the sales customer table, right? Just by, I would say, creating a foreign key, we have a much more efficient plan. Let me redo or recreate the foreign key. So the next one is about conjunction. So sometimes we have a predicate with a lot of ends. So you can see product ID between 300 and 400 and so forth. So the query optimizer is smart enough in order to, how can I put it, to simplify the conjunction, because in the end, this is nothing else than product ID 100. We have a lot of overlaps here, and in the end, product ID is nothing else than product ID is equal to 400, right? This will lead to 400. So we can see this in the input tree. I do not want to go to the message window anymore because I copied the part already here. We can see from an input tree perspective that SQL Server has a comparison, a greater comparison and a lower comparison. And we can see all the values here, 300, 400, 200, and so forth. So in this simplified tree, we can see that SQL Server is smart enough to detect that in the end, this will lead to product ID 400, right? Because sometimes you wonder whether it is worth to rewrite your where predicates. You do not have to, right? So this is a disconjunction, and it works exactly the same. So in the end, the predicate will lead to product ID between 200 and 600, which is pretty easy because when you have an OR in your predicate, this is always the minimum and the maximum. So, and again, SQL Server is smart enough to detect these kind of the disconjunction and evaluates the product ID or the predicate, rewrites the predicate, and looks for product IDs greater than 200 and lower than 600, right? Lower, greater. That's it. So again, SQL Server or the query engine is really, really smart. So another example I will show you is about check constraints. So I have a check constraint on the table production product. And there's one check constraint which has the definition like list price has to be greater or equal to 0, right? For the product production product table. So when I now ask SQL Server to look for rows within the production product table where the list price is less than 100, and I execute the query, SQL Server can easily detect that this is not possible because the check constraint already ensures that this condition can never ever be true. So instead we have a constant scan. So constant scan is, I would say, an operator which costs almost nothing and just creates the column headers for you because we need to have an empty result. Product ID, the name, the product number, but nothing else. So you can see that the overall cost is, I don't know, is really neglectable. So it will not touch the table. So therefore, it is really one of the easiest plan. It is really, really cheap. So again, so it is worth to implement foreign keys, and it is also worth to implement check constraints whenever it makes sense. So then we have something which is called contradiction detection. You can see this is a contradiction. 1 cannot be equal to 2. So this is a contradiction. And again, SQL Server will use a constant scan. So it will not scan the production product table for you. You can see this in the input trees, in the simplified tree, that in the end we have a constant table get, logical operator, and this is in the physical operator, the constant scan. Okay, the next one is about trivial plans. A trivial plan is a plan where we do not have an alternative. Think about a cluster table or a heap without any kind of index. When I have a cluster table without any additional index, the only way, and really the only way to select data from the table, even with a predicate, is to scan or to seek for specific values, depending on whether you have the index key column in your predicate, in your where predicate or not. So there is no alternative, so therefore this is considered to be a trivial plan. So let me do the following. I will just select product ID, name, and product name, product number from the product table. When I execute the query, we can see in the output, this is considered to be a trivial plan. We can see the information in the execution plan as well. It is optimization level trivial. So trivial means SQL Server can entirely skip all the query optimization because there's only one way to execute the query. So, and this is a a very good thing because SQL Server do not have to spend CPU cycles, and for sure, which will lead to a longer elapsed time, so query execution time. So it can completely avoid this kind of query optimization. So trivial execution plans, again, when you have a lot of trivial execution plans, so the query optimizer is not very busy, I would say. Yeah. So this is an example for a trivial plan. So this one is also a trivial plan because the product ID column is part of the index. So it's a clustered index seek, and there's only one way, and really only one way, to execute the query. You can only seek for the product ID equal to 1 within the clustered index. That's it. It is also considered to be a trivial plan. You can see this. So therefore, again, we can completely skip CPU cycles and also time to optimize the query. So I have another example which I found by chance. I'm looking, it's almost the same query as you can see, but this time I'm looking for products where the class is equal to L, and the query plan looks very, very simple. We have a clustered index scan. We can see this is a residual predicate, but this is already considered to be not to be a trivial plan anymore. You can see the optimization level is full. So, and we will see later on that a full optimization means that we have 3 different phases. And we will see that SQL Server has a specific cost threshold for every phase. And when the cost threshold, or when the estimated cost found within a given time, within the first phase, and the costs are still higher than the cost threshold for the phase, SQL Server will go into the next phase and spend more CPU cycles in order to find a cheaper plan, which hopefully is less than the cost threshold for this specific phase. If it is still not the phase, it will use the next phase, which is the third phase. And after this, you will see a timeout, because it makes no sense to run more and more CPU cycles to find the best plan or a good enough plan, which takes hours, and the execution of the query only takes a few seconds, right? So therefore, we always have to have cost thresholds within every optimization phase. So let's talk a little bit about transformation rules. So we can see we have a lot of transformation rules. I want to go a little bit more into detail. So we have one query which tells you about the optimization rules we have. So in 2016, we had something about 400, 2017, we had 404, and in 2019, we have 420. That means Microsoft is keen on introducing more and more rules to simplify your query. So I will give you an example. So we can easily look for all join rules we have. So we have a nested loop, we have a merge join, we have a hash join, and we have something which is table valued function. And I guess this is a bookmark lookup. This is something I don't know. So we have different kind of logical rules which we can apply, and depending on the logical rules, the SQL Server query optimizer applies and successfully implemented in the plan. SQL Server is looking for the appropriate physical operator, right? So we have the same for hash aggregates and so forth. So what we can do is we can see how many rules and what kind of rules SQL Server applies in order to execute a specific query. So what I'm going to do is I will create a snapshot for the transformation rules for this one. I will execute one query, which in the end is a hash match. This is our query. And I will take a snapshot of the transformation rules after the query is executed. And we will compare the snapshot before and the snapshot after. So we can see that during the optimization, that that SQL Server, the SQL Server engine applies different kind of logical rules. So we can see that one plan alternative SQL Server internally created is based on the hash join, another one on the merge join. So all these kind of different alternatives are compared, and the plan with the cheapest estimated costs is taken. So we can easily see that in the end, SQL Server uses a physical operator, the hash match join, because this is, again, the cheapest plan. But all the other rules SQL Server have in place, and they make sense, are applied to find the good enough plan. So what we can easily do is we can use a query like this. So we have an execution plan. Again, it's the same. So we have an index scan, we have a hash match, and we have another index scan. So now we can do the following. We can disable the transformation rule for the hash join. So I just want to make sure, yes, it is disabled. And when I now execute the same query as before, you can see that SQL Server is not allowed to use the hash join anymore. So therefore, the next cheapest alternative is taken, which is in our case, the merge join, right? So I can easily disable the merge join, then we can see that the last alternative is the nested loop join, right? So there's one trace flag in order to see which kind of rules are applied to find the best plan, which is query trace flag 2373. And we can see that we have a lot of different plan alternatives. And this already tells you how many rules SQL Server can apply just to satisfy or to find a good enough plan for this query, right? This is what SQL Server is actually doing in order to find the best plan for you. Okay, so I will skip this one. We'll skip this as well. So let's talk a little bit about memos. You already understand that there are different kind of alternatives when the query is not a trivial one. So therefore, SQL Server will start the full optimization. In order to compare all the different plans SQL Server found during the optimization, SQL Server will create so-called memos. Memo is a memory structure where all these kind of plan alternatives are saved in order to compare all these kind of planet alternatives in the end, and decide for the cheapest one. So this is the idea of a memo. That is a reason why query compilation not only uses CPU in order to find the plan alternatives, to calculate all these kind of plans, it also consumes memory. So that means the more recompilations you have, the more CPU cycles you have, but also the more memory you take, right? This is something most people are not aware. We are all talking about recompilation and CPU, but recompilation also consumes memory, right? So let's see how it works. So we have a final memo, which is in the end the execution plan, and we have an initial memo. So the initial memo is just the representation of the logical operators. So we can see this with the query trace flag 8608. So, and we can see that we have an initial, I will use this one. We have an initial memo structure, which is again just a logical consideration of the plan. So, and we have different kind of groups, and the group is nothing else than alternatives to get data or to join data. And again, the initial memo only has the logical operator, so therefore we do not have alternatives because we only have a logical description of the physical operator. So, but it is already grouped. So when we go one step further, we can see that we have a final memo. And it's the same query as before. We are just using another trace flag, which is 8615. And we can see that we have a memo here, the final memo. This is the final memo, right? Let me go here, this is easier. So we have the same groups as before, but within the group, for example, we have still the logical operator, which is get data from a table. And we have different kind of alternatives, as you can see, right? And maybe this is a better example. We have a hash join and we have a logical join, operator join. And you can see that now within the group, the final memo will tell you which kind of physical operator in the end is applied depending on the costs. So you can see the costs here, right? This is the costs. And the costs are again depending on your, this is a cardinality. That means if you have stale statistics, when your cardinality is not accurate, the query optimizer will not create the best plan for you, because everything is based on cardinality. Everything is based on your hardware resources. You remember DBCC query optimizer what if? So we have a few hardware depending settings or resources, and we have the cardinality estimation. So therefore, here you can see how important it is that you have accurate statistics. So, and in the end, you can see that we have one final plan. This was the initial memo. And we have the alternatives. We have one alternative because you can easily now go from one group. You can see we have within the group 3, we have 1, 2 physical alternatives. And this is just the initial memo. And so we have one alternative, which is a logical operator join, right? So we can see we have different kind of alternatives, and we have another alternative. So SQL Server found 2 alternatives for the same plan, and in the end, the one with the hash join, that one, is taken. So we can easily verify this one, and this is, in the end, this is the physical plan, the output tree, which is nothing else than the plan which will be cached, by using the query flag 8607, right? So we have different kind of alternatives in different memos, and in the end, depending on the estimated cost, which are based on cardinality estimation, for example, this one is taken. The cheapest one is taken. So a trivial plan has no memo structure, right? So we can see there is nothing available. So SQL Server entirely skips these kind of phases. So in the last 5 minutes, I will talk a little bit about the phases. So when SQL Server goes into the full optimization, as I already mentioned, we have 3 phases available, starting with phase 0, phase 1, phase 2, which means we have 3 phases. So the search phase 0 is something which is used for small queries, typically found on OLTP systems. So then we have search phase 1, which is a quick plan. So here we can see that the query optimizer already considers parallelism. And in search phase 2, this is a more enhanced search phase, spending more and more CPU cycles, and the cost threshold is higher than for search phase 1 than for search phase 2. And here SQL Server will apply more and more rules, more and more simplification in order to find a good enough plan within the cost threshold for phase 2, right? So and again, if there is no plan found, which is cheaper than the cost threshold for phase 2, we will see a timeout. So we can easily see, and this is when you have or the other way around, when you have your SQL Server in front of you, you can use this dmexec query optimizer info in order to see how many times a SQL Server will apply search phase 0, 1, or 2. There's a lot of good information in the query. So you can see, for example, the timeout. So when you can see a high number of timeouts in your SQL Server, this is already a hint that you have a lot of plans they are running into a timeout. That means SQL Server was not able to find a so-called good enough plan, even within search phase 2, which is cheaper than the cost threshold for search phase 2. That means your plans are so complicated that SQL Server will stop evaluating or comparing different kind of plans and just takes the cheapest one which is available at that point in time. But this is never ever the good enough plan. So I have one example here because I'm running a little bit out of time. Skip this. Let me go to the one with the timeout. I need to go down. Here we have one query. This is a query. It's a very complex one. So, and we can see that I do not need to execute the query. I just need to see the estimated plan. This is so annoying. Sorry for this. We can see that this query plan is full optimization, but reason for early termination of statement optimization is timeout. What you have to understand is that when you have a plan, and I executed the query before, and even I do not need to execute, just looking at the estimated plan, there is already a plan in cache. When I try to find the plan in cache, there is no plan. That means whenever you have query plans running into a timeout problem, SQL Server will not cache the one. I had one customer, they were wondering about the high recompilation. That is because but a lot of plans were marked as timeout. That means for every new execution of these kind of complex plans, SQL Server has to recompile a new plan, which is again not part of the cache. That means these kind of CPU cycles you spend for the first compilation, it's completely makes no sense, because the next execution of the same query will force SQL Server to optimize the query again and again and again. That can be a reason why you have a lot of CPU caused by, or CPU consumption caused by queries running into timeout. So there's one query, I know I have only 1 minute left, which you can use in order to find plans with high compilation hardware consumption for compilations. And this is a very good one because we can easily see the hardware consumption for query plan compilation. This is compilation time, CPU cycles, memory, and all the other information you need in order to implement the right index to simplify the execution plan. So I think that's it. I'm a little bit running out of time, but if you have any kind of question, feel free to ask. I think we have at least 10 minutes until the next session starts.
Okay, so far there are 2 questions, but about the same thing.
Okay.
If there's any location where the attendees can download the scripts.
I will upload the session. Yeah, I will upload the session. Yes, and you can download the session then.
Okay.
Any other question?
So far no, but let's wait a little bit.
Yeah, if not, you can always drop me an email.
And there's another one, but just to say thank you to you for the opportunity to listen to this session on the interesting aspects.
Welcome.
another thank you and great presentation coming up.
Okay, if not, again, just drop me an email if you have further questions, and I promise to upload the session so everyone can go through the code, because I can imagine it was fast, but you have a chance to, yeah, to replay the session and try it on your own.
Okay, so there's so far no new questions, so I think we can just close the session. So thank you, Torsten, for joining us and sharing the knowledge.
Thanks. Thanks for giving me the opportunity to speak at SQL Day in Poland. Okay, then have a nice day.
Thanks to all and have a nice day, Torsten.
Cheers, bye.